So in the previous lecture, we have analyzed this uh, cascade transistors and their output impedances. So what we have seen is when you use two cascades, for example, like this one behaves like the source or degeneration resistance with a high value of RO2. So when you calculate it, when you find the expression, this one will become negligible, and you can simplify the whole thing like this. When you increase the number of cascades to a number of n, you keep increasing the resistance, and you can achieve very large output resistances. The only limitation is, of course, the voltage swing, or the voltage required to keep all the transistors in saturation. As long as you have enough voltage, you can connect many transistors in cascade to achieve a very high value. By the way, I noticed that there is something wrong in this expression, so please correct it. Maybe a better writing can be, instead of n, I can say 1 in here. We can start I from 2 and end around n. So correct expression will be RO1 multiplication of GMI and ROI from I is equal to 2 to n. They are basically the same, but the main difference is, of course, this M1 transistor has its output resistance, I guess, in here, but not GM, but the others will have the GM over there. So this is the correct version. Please note it in your notebook. In the previous lecture, I gave you an exercise on bipolar transistors, and you were supposed to find the output impedance of this bipolar cascade, and I told you that there will be some limitation. Did you have a chance to take a look at it? Can anybody find the maximum output impedance for this bipolar cascade? Okay, I guess you forget it. So let's solve it together then. And let's start with the easy, maybe I can do it in here with a new page. So let's think about a simple case. When you have only bipolar transistors with some degeneration resistance, let's call it as RE. I'm trying to find the output impedance in here. So when you draw the small signal equivalent, collector, base, and emitter, when you draw the small signal equivalent circuit, let's say this is Q1, RO1, GM1, V pi1, collector, base, and emitter. Base is grounded because you have DC bias. At the emitter, we have RE. At the collector, what I'm gonna do is I'm gonna put a test voltage, Vx. I will try to find Ix in here. So when you write the expression, this Ix is also passing through here, please note it. So I'm gonna find the potential drop in here, and then I'm gonna find the potential drop in here to find Vx. So Vx will be RO1 times Ix minus GM1 V pi 1 plus RE in parallel with R pi or R pi 1 times Ix. Please note that I didn't use reflection here. That's one of the critical things, because you know, sometimes you may say that R pi is at the base, this thing is at the emitter. So I know that the base current is beta plus 1 times less than the emitter current. So I should use reflection. In this case, no, because you are looking from the collector end, and this GMV pi is already doing that for you. It's already inside the expression. So you don't need to do any reflection. So you can treat this thing like a basic 201 circuit. You just apply KCL and KVL. That's it you need to do. And then I continue solving this thing. I need to find V pi in terms of Ix. In fact, V pi 1 is equal to minus Ix times Re in parallel with R pi 1. So if you put it in here, this will be R01 Ix Re in parallel with R pi 1. Sorry, I make a mistake, I guess. One minus GM1 is going to be plus then Re R pi 1 plus Re R pi 1 Ix. So Vx divided by Ix will be, which is around equal to this term is R01 times something larger than 1, which is a huge impedance, of course. This thing is Re in parallel with R pi 1. R pi 1 is in the range of kilo ohms, which is definitely much smaller than R01. So you can ignore this part. This part is negligible. So I can say that this is approximately equal to R01 1 plus GM Re R pi 1. So when you compare this thing with the MOSFET case, the main difference is this R pi 1 impedance. For the MOSFET case, we don't have it. It's infinite. You know, if you ignore R pi, everything is exactly the same. But unfortunately, we have R pi. So this R pi is the limiting factor. Now assume that I make the circuit in cascade. Many of bipolar transistors are connected, let's say. And I'm trying to find R out. In this case, what I am doing is this part is behaving like, you know, this thing replaces RE. And in fact, since you are using Cascade, of course, this thing is much, much larger than RE. So what does this mean? This means that I am replacing a very large value instead of this RE. It looks like that the output impedance is increasing. But at some point, if you keep increasing RE too much, this R pi is limiting. I mean, this parallel combination cannot be larger than R pi, of course. And at some point, this thing will be quite close to R01 times 1 plus GM1 R pi 1. And at that point, R out will be equal to R01 times 1 plus beta. So this is the upper limit that you can achieve. This is the maximum R out. You can put like maybe hundreds of cascades in bipolar transistors, maybe thousands of them, whatever you do. This is the maximum value of R out that you can achieve with bipolar cascades. Is it clear? So for the MOSFET case, we don't have this term, so you can increase it as much as you can as long as your voltage headroom is high enough. But for bipolar one, there's an upper limit. Our output resistance cannot be larger than beta plus 1 times R01. So any question up to this part?
Hocam ben bir soru soracaktım.
Tabii.
MOSFET'in Cascade formülü sanki eski hali daha doğruydu diye düşündüm de. Bakabilir miyiz diyecektim.
Okay, let's double check it. So let's try to do it with this two transistor case. Let's double check it, whether it is matching or not. So we have all the arrows, but yeah, you're right. No, GM1 is missing in here. Maybe GM1, we have to keep it over there. Yeah, I guess you're right. So this correction is meaningless. You're right. Okay, so previous version is correct, in fact. Thank you for the correction. This is the correct one, okay? So let's continue working on a bit more complicated circuits. Let's say that we have such an amplifier. When you take a look at it, the AC signal is supplied from here, and one transistor is the amplifying transistor. M2 and M3 has no AC on the gate, so they are just behaving like load resistances. And I am trying to find the overall gain, V out divided by VG. So what I should do is, as you see, this node is AC-wise grounded. Therefore, this VG is appearing at the gate VGS of M1. Therefore, ID current can be written as GM1 times VG. Okay. What I need to do is I need to find the total AC resistance at this node. And this AC resistance has two components. One of them is RO1, node degeneration. For the upper one, these are PMOS transistors, two cascade PMOS. So you can write the other resistance as GM2, RO2, RO1. Sorry, RO3, of course. And this thing is RO1. So you are going to take the parallel combination to find the overall gain. And in that case, the value will be GM1, RO1 in parallel with GM2, RO2, RO3. Of course, we shouldn't forget the negative sign in here because the current is going in the reverse direction. So what you're doing here by using cascade at the upper path or upper leg, you increase the resistance at the upper leg. So you improve the gain. But of course, this is not the best design. This is not a well-optimized design. Why? Because at the bottom leg, you still have only one transistor. The output resistance at this leg is low, so it is limiting. So if you want to benefit from the advantage of cascade, you should use it in a symmetrical way. I mean, if you use cascade at the upper part, you should use cascade at the bottom part to match the output impedances and to achieve the largest output impedance out of this structure. So in that case, a better design will be this one. Why? Because again, the same story. Only this transistor is amplifying. The others are all loads. VG is applied in here. So what I do is the current passing through here, ID can be written as, since this node is grounded AC wise, ID can be written as GM1 VG. And the same ID passes through here. Keep in mind that this M2 transistor is a common gate amplifier. It's a current buffer. Whatever you have at the source end will be transferred to the drain end. So that ID will be exactly the same. So it only passes the current to the upper part. And then I need to write these two components. This one is straightforward, GM3, RO3, RO4. And the resistance seen in this part will be GM2, RO1, RO2. Now I have that cascade structure at the bottom. So you can write the overall gain as minus GM1, GM2, RO1, RO2 in parallel with GM3, RO3, RO4. So now I have more balanced output impedance. Upper path and the lower path sees similar impedances, so you improve the gain significantly right now. So the gain improvement is significant. But there are two things that you should be careful. The first thing is, now the minimum value for VDD is increased. Why? Because when you take a look at the previous circuit, on this line, you have 3 transistors to keep in saturation. So you have to provide this VSD voltage drop requirement for saturation operation. The same thing for this one and the same thing for this one. But in this case, you have 4 transistors, 1 transistor more. So the minimum value for the VDD is increased. You have to keep all the transistors in saturation. Please don't forget that. We have to keep all transistors in sat for proper operation. That puts a limit in the minimum value of VDD. The second thing is, it is very important to decide on which transistor is the amplifying one. We should apply VG to the correct transistor. What does this mean? So when you apply VG at the gate of M1, you have this much amplification. But if you apply VG in here, then you may be in trouble, because then you will see some degeneration resistance in here, and your gain will decrease significantly. Or the same thing, I mean, if you apply VG in here, you will see a degeneration resistance in here, the gain will decrease. You can apply VG in here though, because source amp is grounded, so you will probably end up with the same result. Of course, instead of GM1, you will have GM4. So you should choose the amplifying transistor properly. So here is an example. For this particular case, assume that we apply VG at the second transistor gate. Now the story changes. Why? Because this one, this M1, will be treated as RO1 when you take a look at from M2, source of M2. And therefore, when you try to write this ID, that ID will be different. This ID will not be equal to GM2 VG, but it will be equal to GM2 divided by 1 plus GM2 RO1 VG. We have degeneration. This RO1 behaves like degeneration resistance. Then, of course, the rest is the same. You should multiply this current with the total AC resistance The AC resistance in here is GM3, RO3, RO4. The AC resistance in here, GM2, RO2, RO1. Yeah, the output impedances are the same, but the overall gain is decreased by the degeneration resistance, which will be then minus GM2 divided by 1 plus GM2 RO1 times GM3 RO3 RO4 GM2 RO1 RO2. This part is the same. This part is decreased compared to previous amplifier structure. So where you apply the AC potential significantly matters. So you have to be careful about it. Any question up to this part? Anything you want to ask?
Hocam
Okay,
bu
so
hangisinden AC vereceğimizi duruma göre mi seçmemiz lazım yoksa direkt ikinci transistöre AC vermenin hiçbir faydası yok mu?
it depends on the application. If you want to achieve large gain is of your concern, you have to apply the M1. But in some cases, you may prefer degeneration. You may want to sacrifice from the gain, but on the other hand, you want to increase the bandwidth or something like that, for example, then you can use degeneration. You can use the gate of M2 for AC amplification. We will see such examples, especially in differential amplifiers. These are like single input, single output amplifiers, but of course the same idea can be applied in differential pair. Yeah, depending on the application, you can change which gate you are going to apply VG.
Teşekkürler.
Okay, so we have reviewed the material from 311 very briefly, and we add some new stuff on top of it. But now let's start with the main goal of this course. In this course, we are going to design an op-amp, as I told you in the previous lectures, and an op-amp has many transistors, in fact, has many stages. So we will consider all these stages. And in fact, each individual stage can be used in another analog block, like a comparator, for example, or some other thing. The first thing that we should have is, of course, a biasing stage. Why a biasing is important? Because you are using a supply in here. This supply can be provided by a DC regulator, for example, coming from some AC source. So if there are some variations over there, it's going to affect this supply voltage. And when the supply voltage changes, all the individual transistor parameters will change, and the amplifier gain and other important parameters will change, which is a bad thing, of course. Or if you are using a battery for supplying VDD, as time goes on, the battery voltage will decay down, and VDD is changing, then it's again a problem. The op-amp may perform differently. So what I need to do is, although this VDD changes, even if the VDD changes, inside the amplifier, I should have a reliable and not changing biasing. So biasing stage should be definitely temperature independent. Sorry, not temperature independent, but supply independent. It should be immune to supply variations. That's one thing. The other thing is the temperature may change. And if the temperature changes, for example, the inside transistor parameters may change. If you are using, for example, discrete resistors or resistors, their value will change, and it's going to affect your op-amp performance, which is not tolerable, of course, because the environmental temperature may change during the operation. Even if you try to keep it constant, your op-amp may heat up, and because of the heating, temperature will change, and it's going to affect your op-amp performance. So temperature independence is another important parameter. So initially, we are going to work on this block. We will try to have a biasing structure which is both supply independent and temperature independent. If we can achieve this thing, you can use this biasing stage for many different purposes. You can supply any digital or analog component with this biasing stage. Before continuing, let's give a very short break for 10 minutes, and we will continue with more discussion on this biasing stage.